everyone. Thank you very much for your patience as we're working through some technical difficulties, but we got it all solved in time. Well, thank you. Thank you. It's really teamwork. So yeah, it was a little bit stressful, but we're all good. Welcome to the public lecture hosted by KIPAC, the Kavli Institute for Particle Astrophysics and Cosmology. My name is Sinan Du. I am the Outreach and Engagement Manager here, and I will also be your main host tonight. It's wonderful to see all of you here in person, especially on a rainy day, for our first public lecture in 2026. And we also welcome the similar size of a group online who's watching the YouTube live. And that's why we were trying to get the camera to work for them. So given this is a public lecture in a hybrid format, we are very excited to bring you all, regardless where you are from, to learn something new, and especially today from our newest faculty member at Stanford in the physics department. So before we start, I wanted to quickly share that, we're especially excited to share with you and introduce you to tonight's lecture because Oliver, which I will also introduce just in a second, he joined us last fall. So he's really the newest faculty member at KIPAC in the physics department, as well as the Institute for Theoretical Physics at Stanford. And tonight, you will be learning a little bit more about the early stages of the universe, specifically related to cosmic inflation, and also how we can use galaxies as critical clues to infer about very early on a very key, but still not very well understood phase of cosmic time. So before we get started, I wanted to give a quick shout out to the entire team supporting tonight's event. Those include the front desk staff, which you already met, the AV team who worked very hard to get this to work, as well as Leon, who is helping with managing the live stream. And we also have some chat moderators who will be managing the chat online, and they are all subject matter experts for this topic. So I will have them quickly introduce themselves and say hi. Okay, so great. First we have Bea.
Hi, I'm Bea, or Beatrice Tucci. I'm currently a postdoc at both.
Sorry, one sec.
Okay.
Bea, try again.
Hello.
Good.
Hi, I'm Beatrice Tucci. I'm currently a postdoc at both KIPAC and LHP, and I work on topics very closely related to what will be discussed in the talk, so looking forward.
Great. Thank you very much, Bea. And for the other chat moderators, you may notice that they're actually in person today. So one of them is Cooper Jacobs. So yeah, Cooper is also here in person. He's a first-year graduate student in physics, currently working with Oliver. And last but not least, we also have Bernie, also joining us in person. She is actually a senior graduate student at KIPAC, have been working on many Galaxy surveys, including Rubin and DESI. So both of them will also be available for chat afterwards in person if you like. And all three of them are going to be online to answer any questions. So for those of you joining online, please feel free to use the online chat box to ask any questions you have in mind and engage in discussions. Most of the online questions will be answered by our chat moderators, with a few remained saving for Oliver to answer during the Q&A. And for all of you in person, we kindly ask you to save the questions until the Q&A session at the very end. And Oliver, I promise you guys, he won't leave this room, before answering the last questions. All right, so now it is my greatest pleasure to introduce tonight's speaker, Professor Oliver Philcox. Oliver is an assistant professor here at Stanford who uses data from big experiments and collaborations to tackle some of the most difficult and biggest questions in the universe. So specifically, his research combines theory computation and also data analysis to characterize different physical properties of the universe, including its expansion, its composition, as well as its initial state. So Oliver is originally from the UK. He did his PhD from Princeton and also did postdoctoral research work at Columbia. He loves solving math puzzles, and that's also what initially drew him to astronomy and also remains one of his key motivation in research today. So without further ado, let's welcome Oliver.
There we go. Fantastic. Excellent. Well, thank you, Sinan, for the extremely wonderful introduction. It's my real pleasure to be here and to tell you a little bit today about some of the most exciting aspects of physics from my point of view, and to give you a little flavor about some of the really novel research that's going on just a couple of buildings away in KIPAC in Stanford. So I'd like to start this talk by transporting you across space and time, taking you not back to the beginning of the universe, but to somewhere a little closer to home. In particular, New Jersey. In 1964, two radio engineers, Arno Penzias and Robert Wilson, had built a gigantic radio receiver that you see here, a home door receiver at Bell Telephone Labs. And they had built this receiver in order to have radio communications, and when they turned it on, they noticed something strange. Wherever they pointed their receiver, at any time of day or night, there was a hum. Their receiver was picking up the strange source of radio waves. And this surprised them. It was completely unexpected, and no one knew where it was coming from. Eventually, after days of searching, they finally discovered the explanation. The radio waves were sourced by two pigeons, which had nested in the side of the detector. This is a true story. After removing the pigeons and the pigeon droppings, they then discovered, in fact, that the signal was still there. So what was this mysterious signal? Well, this signal is really central to inflation in cosmology and a lot of physics as we know it today. So this radiation today is known as the cosmic microwave background. It's an abundance of radiation hitting the Earth from every single direction, from north, east, west, south, at all times. It's radiation with a wavelength of around 3 inches or 7 centimeters. And it's exactly the sort of radiation that something would give out if it was extremely cold. Looks like sort of you're staring at a little blob of gas at around minus 455 degrees Fahrenheit. So that's pretty cold. This is about 400 degrees colder than winter in the rest of the US. So what is this? It kind of looks like, well, the universe is just sort of glowing. It's glowing at this really low temperature. It turns out that just a couple of tens of miles away in Princeton University, theorists had already been thinking about very similar radiation. And it wasn't for a few years that the two groups were put in contact. And it was discovered that this radiation really was something of great physical insight. And this discovery by Penzias and Wilson eventually won the Nobel Prize in 1978. So what is this radiation and why is it exciting? So to understand it, we're going to have to go and do a brief little diversion into cosmic history. So here is a picture of the universe we see today. This is a real picture, I think taken by the James Webb Space Telescope, of the universe at age today, which is about 14 billion years old. It's actually by Euclid, not James Webb, apologies. And today the universe has a size of around 46 billion light years. And that's the size we can see. The universe could be much bigger, but I'm just talking about the stuff that we can physically interact with, all the stuff that gets to our telescopes today. If we take this picture and wind back time a little bit, we get a universe that looks a little bit different. If I wind back from 14 billion years to 6 billion years, then the universe is twice as small. If I wind back again 2 billion years after the Big Bang, it's now another factor of 2 smaller. And I could continue going and going and going. And the real point is that the universe has spent its billions of years evolving and growing. And we know very well today that the universe has been expanding and expanding for billions of years. So if I was to reverse this clock, we would see that the universe was getting smaller and denser and hotter. And this point of it being hotter is particularly important. So it's kind of like if you pump up a bicycle tire. Your bicycle pump is going to get hot because you're trying to squeeze the same amount of gas into a much smaller and smaller space. And as a result, it heats up. And the same thing's true in the universe. A universe at 3 degrees today would be 6 degrees 6 billion years ago, 12 degrees here, 24 degrees here, etc., etc. And why is this interesting? Well, it's interesting because you can continue this picture much, much, much further back. And you get a universe which is even much, much hotter still. So let's imagine we trace back the evolution of the universe until it was almost 3,000 degrees hot, or 3,000 Kelvin, or 5,000 degrees Fahrenheit. Once we get this early in the universe, something strange happens. The universe is so hot that atoms can no longer stay connected together. Atoms made of protons and electrons become dissociated. The protons and the electrons no longer combine together, and they're all whizzing around in the universe. The technical term for this is a particle soup. This is a technical term, I promise. So at this point, we have a universe consisting of protons, electrons, and some neutrons flying around as well. The only other component that we care about in the universe is light. We have a whole bunch of light, which is trying its best to kind of stream across the universe, but it's not getting very far. Whenever the light tries to go anywhere, it immediately bumps into an electron, bumps into a proton, etc. It's like me trying to walk through this lecture theater if everyone is running around. It's very hard. Something strange happens when the universe is around this particular temperature of 3,000 degrees, or an age of 380,000 years. And that's that the universe spontaneously cools down. As I say, as it's evolving, it's getting older, it's getting cooler, and at some point, we're going to reach a point where these protons and electrons, which were busy jumbling around and no longer combined together, are suddenly going to combine. The temperature has cooled down enough that it now becomes their best option just to combine together in a lower energy state. They no longer have energy to run around. And then they form hydrogen. It's like the simplest chemistry equation ever. Proton plus electron is hydrogen plus photons. And now you can ask, well, what happens to all of these little photons? Well, these photons, which previously were trapped and previously bouncing between protons and electrons, suddenly can now stream fully. It's like me trying to run through this lecture theater right now. Now everyone's sitting down in a very ordered state. It's extremely easy to move across the system. And as a result, at this very particular time, 380,000 years after the Big Bang, there is an incredible amount of light streaming everywhere in the universe. And these photons essentially are released here and will just travel throughout the rest of the universe for the next 14 billion years, no longer impeded by little scatterings. So these photons are the cosmic microwave background. These photons are precisely the ones that Penzias and Wilson detected in their detector in 1964, and we can still detect today. So this picture has been really resolved to much, much greater depth in the intervening years since the 1960s. In 1990s, they sent up a satellite, the COBE satellite, to observe this cosmic microwave background radiation. And by this point, we had some pretty good predictions of what it should look like. In particular, we had predictions for how it should depend on wavelength. It's like how much brightness would we have for each wavelength? This is just a pretty simple prediction for saying, we think the universe is about 2.7 degrees. This is how much radiation we should get. And what you can see is a really exquisite match of theory and data here. The red points match the data, the green line essentially perfectly. This again won the Nobel Prize, now in 2006. So this is a really beautiful map of the radiation coming from just 380,000 years after the beginning of the universe. But it turns out it has some surprising subtleties. The CMB, temperature that is measured by satellites like COBE, is extremely constant. This is a map of the temperature across the entirety of the sky. And you see wherever you look, this temperature is almost exactly the same. It goes from the blue bits here are 2.7 Kelvin minus 0.003, and the red bits are only a tiny, tiny bit hotter. So we've got a universe which appears to be uniform to 1 part in 100,000. And it turns out this is a very surprising result. So let me now tell you why this is so surprising. And to do so, we're going to conduct a little experiment thinking about 2 points on the CMB. 1 point A, if I'm looking, say, over to the north of the CMB, and 1 point B. I'm pointing my satellite in the other direction, looking to the other corner of the universe. So today, these photons have traveled billions of light years to reach us. They've started out in the early universe, traveled throughout time, and hit our detectors today. And the universe today is a fun place. It's traveled through a whole bunch of cosmic structure to get there. But the universe, when these photons set out, was very, very different. In particular, these photons set out in the universe when the universe was much, much smaller. They started at an age of just 380,000 years instead of 14 billion. And this has a surprising consequence. In particular, these two photons, these 2 points at A and B, were so far apart that they had no way of talking to each other. So what do I mean by talking to each other? I mean that if some guy standing at A was to decide, hey, I want to send a message to my friend at point B, there was no way he could possibly have done so. Because if it tried, he would have sent out his little, I don't know, carrier pigeon or electron pigeon or photon pigeon or however he wants. And the furthest the signal would have got is just the edge of the universe there. It couldn't have got to point B simply because the universe just hadn't expanded enough yet. The universe was so small that there was no way to get information from A to B. And this brings about a surprising paradox. If these 2 points could never have talked to each other, then how come they have exactly the same temperature? How come the CMB we see from A and B is almost precisely uniform to 1 part in 100,000? This is actually really surprising. Like, I like to think of this with a little bit of an analogy. Like, imagine we look around the room today and we discover that we discover that I'm wearing, I don't know, bright green socks. You think, okay, that's fine, nice. That's a strange fashion choice, but okay. And then you discover that everyone else is also wearing bright green socks. Then you say, well, either everyone in this room has very strange fashion choices, or there was some way that we all were in communication. We all told each other that we wanted to do this. The chances of this happening at random are so infinitesimally small, this would never happen by chance. And this is really exactly the same thing in the universe. It's not just the case that these 2 points have the same temperature. It's the point, skipping the conclusion here, it's the case that also points at the top and the bottom and every possible pair of points I could ever think of all have the same temperature. And that is strange. So how do we resolve this paradox? Well, the solution actually came about from work done just a couple of blocks away from here by a guy called Professor Andre Linde at the Stanford Theoretical Physics Institute. And the solution is known today as inflation. Inflation, at its heart, is fairly simple. It tells us that the universe, very, very, very early on, was much, much smaller. That A and B were actually extremely close together in the extremely early universe. And then something catastrophic happened. The universe inflated and expanded by a huge amount, ripping these 2 points apart, such that they could no longer talk to each other. This immediately solves the previous problems, because now, in the very early universe, A and B could talk to each other, they could tell each other what their crazy green-colored sock plans were. But then later in time, we think, well, that's strange, they never looked like they could have touched. That's because they have this sort of hidden agenda right at the beginning. In fact, to make this work, you need to do some pretty outrageous amount of expansion. In particular, within a time period of a trillionth of a second, we want the universe to expand by a billion times. And those are pretty huge numbers. And you might think, well, this theory sounds wild. I've come up with probably the craziest theory ever just to explain why all the temperature everywhere is the same. This seems kind of unlikely. And the really surprising thing is that this theory, which essentially is just that, an exponential expansion, works incredibly well. So you could think, well, what sort of energy, what sort of temperatures, and what sort of sizes am I talking about here? So in the beginning, this inflationary universe was extremely small. I already said it expanded by a billion times. So you could think, well, how hot would it have been in these days, and how dense? And I think it's useful to compare the temperature of the early universe to other things we know and love. The sun, for example, right in the middle, it has a temperature of about 30 million degrees Fahrenheit. That's pretty hot, but inflation is a lot more. The biggest particle collider we've ever built on Earth, the Large Hadron Collider at CERN, gets to a temperature of about 2 billion degrees. Inflation is much hotter than even this. It gets to a temperature of 200 million billion degrees Fahrenheit, which is pretty crazy by anyone's standards. And an important thing to say here is that at these sorts of energies, these sorts of temperatures, we're dealing with a universe which is super hot and super small. And this is exactly the regime where we have to worry about quantum physics. Quantum physics is the theory of the small and the hot. So naturally, this has to be the theory we want to use if we want to explore inflation. So let's think about this in a little bit more detail. The one thing I know about quantum physics is that it's a theory of randomness. It tells us that nothing is ever completely still. If I take a bit of the universe and I say, cool, let's imagine my universe is completely empty and completely flat and has the same energy everywhere. Quantum physics will tell us, well, that's not quite true. It's always going to be a seething mass of things popping in and out of existence. I'm going to have bits of the universe that have a tiny bit extra energy, and I'm going to have bits of the universe with tiny bit less energy. We have this seething mass of quantum effects, which is a generic prediction of any quantum theory. And imagine taking this quantum universe and now expanding it by some exponentially large amount. This tiny seething mess of quantum fluctuations is now going to be stretched into huge, large-scale fluctuations in the universe. In particular, we could think, well, what's the temperature of the cosmic microwave background going to look like? What we're going to find is it's actually really related to this. A quantum fluctuation upwards in the early universe gives us a little bit more energy. If we stretch that out, we're going to end up with a CMB with a temperature which is slightly higher. Slightly less energy in quantum physics is going to give us slightly lower energy at the time of the CMB. This is a surprisingly useful prediction because it generically predicts that the CMB we see should not quite be uniform. It should almost be the same temperature everywhere, but it should have tiny little fluctuations. And this is a prediction that's been confirmed by generations of experiments. Starting from COBE that I mentioned before, we've had new data in the 2000s from the Wilkinson Microwave Anisotropy satellite, as well as the Planck satellite in 2010, and now a whole host of ground-based instruments, including ACT and SPT. And essentially, by combining two things together, which is inflation exponentially expanding and inflation having quantum physics and quantum fluctuations, we can predict what the CMB looks like, just feeding in a little bit of knowledge of electrons and protons and little nuclear reactions that happened when the CMB was emitted. What we get out is a prediction that matches the data extremely precisely. So this is kind of the killer plot of the CMB that people really love to show. And let me just tell you for a second what it means. So this is essentially a plot of how much is my CMB non-uniform. So this is a plot of the temperature on the left-hand side here. Red bits are hot, blue bits are cold. And I can say, well, how are these points related? If I take 2 points together, what's the probability that both of them are going to be hot or both of them are going to be cold? And I can say, well, let me make a plot. I can make a plot of the average temperature for 2 points, say separated by a degree, separated by half a degree, tenth of a degree, etc., etc. And we've been making these plots at extreme accuracy. This is one from, I think, the Planck satellite here. And you can fit your model to data, which is really just atomic physics plus inflation. And we find this incredible accuracy. And to me, this is the best proof we have of inflation. This was a prediction that came before the observations. This predated even the first satellites. And yet you can see it matches to exquisite agreement. So of course, inflation is not really the only model in town. In the last 50 years, there's been a whole host of models proposed to explain the anomalies we see in the early universe, why it's so uniform, and why it has tiny little fluctuations above this uniform thing. But really, from my point of view, inflation has been the winner. It's been the model that fits the data the best, with really the minimal number of assumptions. So what do we actually know about inflation? Well, it's really only two things. It's an exponential expansion, and it's a quantum fluctuation. That's it. So you could, of course, ask, well, what do we not know about inflation? And that list is quite a lot bigger. How did inflation begin? Why do we have expansion? What caused it? And even more fundamentally, what were the laws of physics that could create such a crazy phenomenon? And as I've said before, inflation is a phenomenon that's happening at ultra high energies. So if we're studying it, we're directly able to probe physics at these high energies. And these energies are so much higher than anything we could ever hope to probe on Earth. In particular, let's imagine you wanted to probe inflationary physics with a particle collider like the Large Hadron Collider at CERN. We would need to take that collider and we would need to increase it in size so much that it went from Switzerland, where it now starts, all the way to the next star and back again. I don't think we're ever going to be able to build that big an accelerator. So for now, studying inflation is probably our best bet to solve high energy physics. So how do we actually do this in practice? So to me, there's kind of a couple of step procedures. And one of the big questions we want to ask is, well, what are these laws of physics that explain inflation? And that seems like a big sort of vacuous question. And I think to really understand this, it's worth taking a look at the laws of physics we already know and love. So the standard model of particle physics has been developed since the last century or so, and it basically says that the universe is contained of two different sorts of things. There are particles, the electrons, quarks, neutrinos, protons, neutrons, etc., and there are forces, and there are ways for these particles to interact. You have the strong force, the weak force, gravity, electricity, magnetism, electromagnetism, etc. So we could then ask, well, what are the analogs of this in the early universe? Do we have a similar looking model? Do we have the same model? Or do we have something much, much different? We could ask, well, how many particles do we have in the early universe? We know we need to have one. We need a particle which causes this whole inflationary thing to happen. But do we have others? In the standard model, we have loads of different types of things. Maybe the early universe is like that. Also, how many interactions do we have? We need one, once again, to make everything expand and push apart. But are there others? Building on these basic principles, just numbers of particles and numbers of interactions, we can start to build models of the early universe, even though we don't know how to access it in the lab directly. It turns out we can do this even more concretely when we actually combine with some other physical intuitions, in particular, a lot of intuition coming from symmetry. So there's a lot of things we expect about the universe. For example, we expect the universe is the same in whichever direction we look. We expect it's the same wherever we look in space. And we expect it's going to be the same wherever we look in time. The laws of physics don't just change overnight. And those sort of assumptions actually really help us constrain the possible different models we could think of in inflation. Okay, so let's imagine we have a favorite model of inflation that we cook up on a blackboard or a textbook or whatever else we fancy. How do we go and actually test if it's true? First thing we do is we take this model of inflation and we go ahead and predict what inflation would actually look like given these laws. This is actually surprisingly easy to do once you talk to enough friends in the theoretical physics departments who've been doing this for many years. Once you've done that, we then take our model of inflation and predict the cosmic microwave background. This bit's really easy. We say lots of energy here in inflation, lots of temperature here in the CMB. Great, straightforward. Final thing we do is we compare it to data. And then we say, great, does our map of the cosmic microwave background look like what we observe? Does it do so in some kind of statistically robust way? If yes, great, we've solved the laws of inflation. If no, we try again. And that schematic picture is essentially what we do to directly probe real direct questions about the nature of physics in the extremely early universe. And fundamentally, this is really running a particle experiment the size of the entire universe, the ultimate particle collider. So at Stanford, we've been very heavily invested within these questions. And a couple of things we've been learning are summarized on this. So a couple of things we know. One thing is that the energy of this inflationary universe is probably less than 20 trillion degrees. That might not sound that impressive, but it's 200 trillion. It's less than 300 trillion at least. It turns out this has been work that's really been pioneered by researchers focused on the South Pole. In particular, I think I had Professor Xiaolin Kuo give a talk in this series a year or so ago, really focusing on how we can sort of make these sorts of measurements. We also know some things about the laws of physics. We think that inflation was probably controlled by just one particle, just one type of particle. And we think that these particles didn't interact with themselves that much. Now, you might be sitting here thinking, well, this is nice, but he's said a lot of probablys. This probably has just one type, it probably didn't do this, and it probably has this temperature. And that's great. So of course, we want to say these things a little bit more definitively. And here, we're really limited, not by theory, but actually by data. So the CMB has been a really beautiful probe of the early universe, but its dominance is really coming to an end. So I've previously been telling you about 3 sets of experiments, COBE, WMAP, and Planck, which had mapped the universe to increasing and increasing precision. Of course, there are new kids on the block. There are new experiments, such as the Simons Observatory, which Stanford and SLAC have been heavily involved with, which are now mapping the CMB universe from Earth in the Atacama Desert. And these guys are providing beautiful maps of the cosmic microwave backgrounds. But it turns out they're not actually very useful for the kind of particle physics studies we're interested in. They really map the CMB in extremely high resolution. But unfortunately, that high resolution is contaminated by a whole bunch of astronomical effects, like clusters of galaxies and dust in the Milky Way and all sorts of fun stuff that are great for studying astronomy, but don't help us if we want to study the initial conditions of the universe, which are kind of washed out by all this messy gastrophysics. So if we want to go further and turn all these probablys about the universe into certainties, we need a new probe. And this is really what I'm most excited about. The next generation experiment we can use to measure inflation is not the CMB, but it's the universe much, much later in time. In particular, we take our model of the universe, inflation, CMB, and then the history of everything else, and now we look at the end rather than the beginning. We say, can we learn anything about the beginning of the universe by looking at galaxies today? Modern surveys of galaxies have produced incredible high-resolution maps of galaxies in the universe. This here is a picture from the DESI survey, and every single dot you can see here, every pixel, is a single individual galaxy that has been mapped in 3 dimensions. We've got these incredibly beautiful images. I'm a theorist, so I never get to see images, so these are amazing, which you can see, and they have such a lot of structure in. Like just by looking at this, you'll notice that these galaxies are extremely not uniform. You can see there's some areas of the universe which have more galaxies and some areas that have less. And in particular, this holds the key to how we can learn about the early universe. Just as we had bits of the CMB that were hotter that told us about inflation that had more energy, we have the same thing here. Areas of the universe with more galaxies had more energy right at the beginning. That energy sort of evolved over time and it gradually accreted stuff and got denser and denser and denser until we have stuff with more galaxies in it today. Areas with less galaxies, such as this little blob down here, had less energy in the early universe. So if we understand how we go from the early universe to the late universe, we can then turn this backwards and try and learn about inflation from the distribution of galaxies seen today. And at this point, I just wanted to highlight some of the really incredible work done by huge communities of people to get this kind of data set. So this image I showed you there, which is an image of, I think, about 30 million galaxies now, is taken from the DESI collaboration. This is a shot of the DESI collaboration in December 2025, so just last year. So they've been making these incredible maps, which is really involving hundreds of people, only a subset you see here. And now this data is not just used by the collaboration, it's also been made totally public. Anyone who wants can go on the DESI website and download this whole map of where all the galaxies are. It sounds beautiful. It's really just a very large text file of numbers, but still, it's a very fun thing to play with. Unfortunately, if we want to use this data set to learn something about the early universe, we're going to have to be a little bit careful. In particular, we need to really understand the relation between inflation and the statistics we have. So for the CMB, this wasn't too hard. We took inflation, we modeled it forward 380,000 years, and that was it. Now we have to model the universe forward not 380,000 years, but 10 to 14 billion years. And that's considerably harder. You can see this sort of pictures from galaxies on the bottom right has so much more structure than the CMB have. We have to really carefully model a whole host of extremely complicated phenomena in the universe, including the formation of galaxies, formation of black holes, stars, etc., etc. So here at Stanford, we've really been focusing on doing this in a really sort of mathematical way. In particular, we've been focused on predicting the distribution of galaxies and matter in the universe on a blackboard. Essentially, we write down equations, kind of like this thing shown at the top. We say the number of galaxies is some physics times inflation, plus some more physics times inflation squared, plus inflation cubed, etc., etc., etc. That sounds crazy, but this is actually true. Exactly what these functions of physics, that's the hard bit. It turns out, once again, symmetries really help us here. Things we know about the universe looking the same in time, in space, in direction, etc., really, really constrain the possible sets of things that can happen. And of course, it's not quite as simple as this. We do have to use some pretty heavy-duty technology to get here. In particular, we write down a lot of painful integrals involving lots of functions like this one, and then we integrate them using a whole bunch of tools we've borrowed from our friends in quantum field theory. Again, mostly a couple of buildings down the road in Stanford. So this program has really been being developed over the last 10 years. It's work that was awarded the New Horizons Prize with myself and some colleagues, Misha Ivanov and Marko Simonovic last year. And essentially, we take 4 steps. We take the universe in inflation, we predict it, we do some theory on some blackboards to say what happens next. We then throw it to some computers to solve the whole thing for us, solve our equations. Now, I should say the computers are a little more sophisticated from this one. We do tend to use a lot of supercomputers, and Stanford's supercomputer is great for that. And we end up popping out a prediction for what the distribution of galaxies looks like at the end. And why is this fun? Well, it's fun because we can really just put it directly into our little pipeline. If we've guessed the laws of physics, predicted inflation, and then predict the distribution of galaxies, we can then compare it to these beautiful high-resolution data sets we get from surveys such as DESI, and try and learn a little bit more about the early universe. This is a very new and very exciting program. The first results of this, I think, came in 2022. The most recent results, I think, are just probably a month old now. And I think I'm just going to tell you about probably 2 little results in the last couple of minutes of this talk that I think are kind of fun. And the first one is to do with this idea of how many particles are there in the early universe? Do I have just one type of particle or lots? And of course, it would be useful to be a little bit more mathematical here. So I'm going to introduce something I call the inflation particulometer, or FNL if you're an expert, but particulometer is a bit more fun. Essentially, this is some way of quantifying what I mean by this. If this number is bigger than 1, I have lots of particles in the universe. And if it's less than 1, I have only 1 particle. Nothing new happening at all. So this is good, and we can make measurements of the particulometer. The best measurements we have to date are actually from the cosmic microwave background. It's made some really great predictions of this, and it said our particulometer is less than 5. So this is what I mean by we think we only have 1 type of particle. If we could get this bar to somewhere below 1, I could say certainly there is no interesting physics happening from additional particles in my universe. But we're not quite there yet. We're still somewhere near, but not quite there. So how do we do with galaxies? Well, the state of the art in 2022, with some work by myself and some collaborators sort of across the world now, we managed to say, well, great, our inflation particulometer from galaxies is less than 33. And that's actually not very good. The real point here is this constraint is much, much worse than the one from the CMB, and it tells us much less. We really want to either detect something or push these little bars down below this horizontal line. So we're not there yet. So the state of the art now is with this beautiful new data from DESI, we're able to do much, much better. So the hot off the press results, which were released in December last year, was we managed to predict and measure this guy from Galaxies at really incredible resolution. And we managed to get this particle-ometer to less than 7. So you might say, well, this is great, but I said we wanted to beat the yellow curve, and we're still not quite there. And that is true. However, the data is getting better and better and better. In just 3 years, this guy has improved by a factor of 6. So in just another 3 years, we're very likely going to finally be able to hit this horizontal line we get to. We're going to definitively say either we do have new particles in the early universe or we don't. And that is going to happen in, I would say, 3 to 5 years' time, following all these developments. Finally, I wanted to tell you about an even newer result, which I think is kind of fun, which is really a little bit more about what these particles actually are. So there's a whole bunch of more questions we can ask, not just do we have particles? We can say, well, do they interact with each other? Do they have masses? How heavy are they? Do they have spins? Things we know from particle physics. And do they have speeds? So a little test I was doing, in fact, yesterday morning, was to try and detect, in particular, different masses of particles with the cosmic microwave background. Some of this beautiful data I showed you right at the beginning. This is what it looks like. I said, let me take a whole bunch of different types of particles with a whole bunch of different temperatures, all ranging from about 0 to 1,000 trillion degrees Fahrenheit, and say, well, let's look at the data and see, do I detect any of them? And what I can do is, for every single particle I look at, I can say, well, let's see, do I see a real signal? Yes or no? So always I'm going to have some kind of probability of seeing it between 0 and 100%. 0 means definitely, definitely not there. 100% means great, I need the Nobel Prize. What we see actually in practice is basically nothing too exciting yet. So these curves are actually for 2 different types of particles. There's ones that are moving quite slowly, others that are moving quite a bit quicker. And you see that all of these, we have some kind of interesting signals. That could be interesting, but we're not really sure if they're real signals or not. Like it's 50-50. This could be signal, it could be noise. 50-50 is definitely not something you write home about. 50-50 is something you say, give me another 10 years of data, and we can see if this is a real signal. To be absolutely sure enough to claim something is real, we really want to push this to, we've detected it at 99.9996%. That's the sort of 5 sigma gold standard cosmologists love, and we're definitely not there. So in the morning yesterday, I didn't detect any new particles and solve inflationary physics. I still have hope for tomorrow morning. So really at this point, I wanted to kind of finish by saying there's a lot more coming very soon. The DESI survey has been an incredible instrument that's been producing a whole wealth of data. It's now about halfway through. It's been mapping the universe at fairly nearby in the last 6 billion years or so. But we've got lots more experiments coming up. The Euclid satellite, launched by the European Space Agency, is currently in space. I'm currently preparing its first amount of data. That's going to map another 30 million galaxies, much, much older in time, looking back almost 10 billion years. And the generation after that is going to be extremely exciting again. So-called proposed SPEC S5 experiment, or spectroscopic stage 5. I think they really need a catchier title. This guy is going to map now 100 million galaxies, looking back extremely early in the universe. It's going to map galaxies from all the way back to 2 billion years after the universe began. And with this incredible new swathes of data, we're going to be able to test these models I've been talking about to outrageously better precision. And hopefully, one day, we can use these to discover something exciting about the early universe. So at this point, I'll conclude to say that inflation is incredible. It can explain our observations of the cosmic microwave background just by saying we have some exponential expansion and some quantum fluctuations. By studying inflation, we get to probe the universe at the highest possible energy scales. It's like building a particle collider from here to the stars and back again. And now we're able to combine theory and data together to make use of galaxy surveys as an incredible new probe of this, to produce what will very soon be the highest resolution studies and learning the most about some of the most fascinating moments of the universe. So at this point, I'll say thank you very much. I'm very happy to take any questions.
Great, thank you very much, Oliver. Let me just turn the light on. We are going to start the Q&A session, and we are going to start with our in-person audience. And for whichever question you have, I will recite them so our Zoom audience can also hear. Okay, over there.
I was wondering if there's any intuition that you could get about like what the acoustic peaks in the city are, like why specific angles have like more variation.
Great. So the question was whether you can give more insights when you are showing the power spectrum where there's the angular separation versus temperature fluctuation. Why specifically we're seeing a peak around 1 degree? Does that indicate anything?
Yeah, that's a really great question. Thank you very much for the question. So yeah, this is very interesting. And really, this is all to do with this little function of physics going on in the middle here. So what's going on here is, and in fact, I didn't really mention much in this talk, but it's in the very early universe when we have these, this radiation being produced, we essentially have a whole bunch of sound waves. We have sort of little perturbations which can travel and form sound waves, just like we have in the universe today. And these sound waves imprint themselves to, you're more likely to find bits of temperature separated by a certain distance. And that distance is whatever the wavelength of that sound wave is. So essentially, all of these peaks here are just one sound wave, two sound waves, three sound waves, etc. And it's just a set of sound wave harmonics, essentially. This is really what gives the CMB its incredible predictive power. And in particular, it depends on a whole bunch of interesting atomic physics and things like the mass of the electron, which actually allow us to measure them directly from the CMB. Very exciting.
Over there.
My question is like you mentioned a lot about very extremely high temperature. And as a humans, I've never touched anything more than like a few tens of degrees C. How do we imagine like millions of like degrees? What's the concept? Is it just a number you get it from the equation, or is there any concept or theory?
Yeah, that's a great question.
Great question. Yeah. So yeah, the question was, given that all these temperatures that we're talking about is like really astronomical, right? So is there a better way to actually put that into perspective, related to everyday life, or are there any ways even for you to like conceptualize it?
Yeah, that is one of the difficulties with studying inflation, is that everything is extremely hard to conceptualize. It's always wildly large numbers. I think in general, I mean, we're normally thinking about this all in terms of energy, like how much energy does the system have, like how much energy do the particles have, and a lot about size. Like we know the size of the universe, and that really sets what a lot of these energies mean. I think it's really hard because all the scales are so tremendous. It's like the size of the universe is I think it's like a billion times smaller even than an atom. So the temperatures are just extremely vast because it's all compressed into that tiny space.
Yeah, and there's actually another great question from online audience member Naige Zhang, asking, you mentioned the plasma soup, right, at the very beginning of the universe. So like there were protons and electrons, but how did they get there in the first place?
Absolutely. Yeah, so this is actually still a bit of an interesting question. So we know there have to be protons and electrons because we see them today, right? They've got to come from somewhere. If you wind back the universe far enough, you get, okay, we've got galaxies, and then before that, we've got stars, and before that, we've got gas, got hydrogen and helium and all the atoms. And before that, all we've got is the stuff that makes up the atoms. So all we've got is the protons and the electrons. Initially, if we go back even before that, we get the stuff that makes up the protons. We get quarks and electrons. Exactly how they came about is still an active area of research. It's generally known as reheating. There's an idea that whatever fun physics you have in inflation has to somehow dump out all its energy and create these particles. This is still a very active area of research, and so far we don't really know.
So I guess, from from current data, we know they must have been there, but we don't know how exactly they got there. Yeah. Over there at the back.
You have like the age of the universe, but then you have the sign larger.
Yeah.
Than, and then there's big, speed of light, so it's expanding faster than speed of light. What's the implication of that in the physics, physics and other?
Oh, so just to confirm, were you asking, like how does the, oh, yeah, yes. So, right. So we know that, nothing can really travel faster than the speed of light, right? But like in this cosmic inflation phase, it's actually the expansion is traveling way faster than that. So how does that break any physical laws?
Yeah, this is a really peculiar thing about inflation, is that the universe expanded much, much faster than the speed of light. And of course, that sounds like something that shouldn't happen. But really, the point is, nothing can expand faster than the speed of light, meaning no thing. Like no particles, no radiation, nothing like that can happen. But what's really going on here is not actual like radiation or particles expanding, it's the space between them. And there's nothing to say that the space between particles cannot expand faster. That can expand however fast it wants. So Einstein didn't tell us anything about that. And that's the trick we're using here.
Thank you. And then there's another online question from AC asking, for all these cosmological talks, we, talk about dark matter, we talk about dark energy. So like, how does dark matter fit into all this big picture?
Yeah, absolutely. So dark matter is super important here. In fact, if you make this plot of what the cosmic microwave background looks like, and you don't have dark matter in your universe, you're going to get a prediction that looks absolutely nothing like the data. We know it's there. We know it's talking to the regular matter, like they're interacting with gravity. So the gas is pulling the dark matter is pulling the gas, etc. In particular, that's going to change all of these little sound waves we have in the universe, and it's going to change the whole structure of this. So it's absolutely a necessary ingredient in the universe, same as dark energy. If we don't put it in, the model simply doesn't work. So we know it's there.
Thank you. Okay, over there.
What's happening in the universe? Is there any limitation of the expansion?
So the question was based on what we currently know, is there any limitations or boundaries as to like when the expansion will stop, or is there an end?
Yeah, it's a really great question. So the universe really has had a whole bunch of phases. We had at the beginning inflation, this exponential expansion. And then after that, it just expanded for a while, mostly due to dark matter. And now we're in a new phase. We have this mysterious dark energy, which has taken over and causing the universe to expand ever and ever faster, make it accelerate. And the best theory we have at the moment, supported by the most recent data, in particular these galaxies, is that the universe will continue to do that. It will continue accelerating and expanding forevermore. So it will never, ever end. At least that's what we think so far.
Yeah, and actually a related question from Douglas Smith asking, so you mentioned all these galaxy surveys that will help us gain perspectives into inflation. So we know that the Rubin LSST will be doing amazing work. So like, how do you see Rubin actively contribute to this topic?
Absolutely. So the Rubin's a really fantastic program that, for everyone in the room, it's a really fantastic program that's being developed quite heavily in Stanford and SLAC National Lab as well. And it's really going to produce maps in a slightly different way to these DESI galaxies. In particular, it's taking images, like actual photos of, say, about 1 billion galaxies, I think, roughly. So these are a little bit different. So for this DESI survey, it's telling us about the universe in 3 dimensions. It's able to tell us where it is in the sky, but also how far away it is by measuring the spectra. Rubin instead will be measuring all these beautiful images, which basically gives you a complementary way of looking at the universe. It's very, very useful for measuring dark matter and also this dark energy, but ends up not quite telling you as much about inflation. Turns out that extra 3rd dimension is really useful if you want to probe some of this extremely high energy physics.
Yeah, sounds like we just need the right type of galaxy survey to do this kind of work.
Absolutely.
Yeah, all right, over there.
Thank you for the talk. In your work, using galaxies as a probe, Is it more valuable to observe galaxies that are younger or older, and why?
Yeah, related question to what we were just discussing. So in your work, when you're studying inflation, do you typically look at younger or older galaxies, and why are they particularly helpful to solve inflation?
Yeah, so it turns out that for us, mostly the younger ones are the best. So if you can go very young and sort of look at galaxies very early in the universe when they were just forming, the universe is much, much simpler. Like over time, the universe is getting more and more complicated. More and more stuff is collapsing. We're forming more like black holes. The black holes are putting out stuff and messing up all the rest of the galaxies, etc. So the modeling gets more and more difficult over time. So if we can go early, it's much, much easier. So that's really why a lot of these sort of next generation experiments are trying to probe extremely young ones, which will really give us the best insight into these inflationary scenarios.
And we also have a very relevant online question from woman Ramani asking, can you please explain a little bit more about the linear versus non-linear growth of the perturbation? Basically, like for CMB, that's kind of linear growth, but when it develops into galaxies, it just becomes non-linear. So how do we even like try to make sense of that?
Yeah, absolutely. So I can basically describe that a little bit with this beautiful equation of everything we do, which is in the CMB, you only need term number one. You need physics times inflation. For galaxies, we need the second one, we need the third one, et cetera, et cetera, et cetera. And this basically comes about because the universe, as I've been mentioning, gets more complicated over time. We get the collapse of stuff into galaxies. We get the formation of the agglomerations of dark matter, of black holes, et cetera. So these nonlinear effects have to be taken into account very, very carefully. So we need to account for all these higher order terms in a self-consistent manner. And that's really where we're borrowing a lot of tools from quantum field theory to help with, in particular, the idea of renormalization, something that was developed probably in the 60s for a very different purpose, but we can use it for very similar purposes here.
So simply put, linear is like when we only include the linear term, the first term, and nonlinear is like when you're trying to also, fit it with like higher orders.
Absolutely.
Got it. Okay, so the last question.
The single particle that was present during inflation.
Yep.
I presume that's called the inflaton.
Yep.
But you didn't tell us whatever happened to the inflaton.
Great. That is a very well-informed question. So you mentioned in your talk there was probably just one single type of particles, inflaton, and can you maybe explain a little bit about like how it got there as to?
Yep.
Yeah.
So in all these theories, there's a really murky bit just after inflation ends. So we have this 10 to the trillion of a second of inflation, and then we get to the end. And this end is where inflation finishes. The universe stops exponentially expanding. And the idea is that this inflaton particle then decays. It decays away into another set of particles, which eventually will end up decaying into the standard particles we have. So this is the thing that will end up creating the electrons, the protons, etc. So it is what we see today, essentially, just in one different form.
Yeah. Sorry, I know we still have many hands up, but Oliver will be here. And yeah, well, let's give Oliver another round of applause. So before we wrap up the event, I also wanted to quickly introduce some of the upcoming events in case you're interested. So Oliver, if you can help us bring the Zoom window back. Yeah, that's it. Okay, so in early March, we are hoping to host another public stargazing night at the Student Observatory. Fingers crossed for good weather, especially during weeks of heavy rain. So if you want to get notified, simply check out our website or sign up for our mailing list. And we would also like to share that we're rolling out a very exciting initiative for local engagement with the Rubin Observatory. So that means we are collaborating with planetariums, community colleges, astro clubs, and also science museums to actually bring Rubin-related public lectures to a place closer to you. So to start this off, we're actually having a public lecture given by one of the KIPAC scientists on March 6th. That's going to be in the College of San Mateo Planetarium in collaboration with the San Mateo County Astronomical Society. We also have another coming up one on April 23rd. That's going to be in the De Anza College Planetarium, where you will also get to see immersive full dome visuals in there. So all of these events are going to be free, we will also share more information through our mailing list. So finally, we're going to have another regular KIPAC public lecture focused on how to use Galaxy service, which you have already learned a little bit today, to actually help us better learn about the nature of dark energy. So that is going to be another cosmology-focused talk. So if you want to keep up with what KIPAC is doing or be notified whenever we have an event up, feel free to follow our social media and also sign up for our mailing list. So thank you everyone for joining us again. We are going to bring everyone back to the screen just to say goodbye. We will follow up with a very quick email with all the information that we have shared today, as well as a quick survey. We always strive to learn what you want us to present in the next lecture, what we did well, and how we could do better to provide you with a better experience. So thank you all for joining us tonight. Hope you enjoy the lecture. Have a good night, and we look forward to seeing you again.